Hi, I'm Regina, and this is my Physics 2211 Lab 3. For this lab, I'll be talking about the purpose, models and fundamental principles, experiment summary, the experiment itself, the code, discussion, and conclusion. The purpose of the lab was to analyze the star's motion to find the net force on the star for all points in the data using the scaffolded starter code, and to determine the initial velocity needed for a spaceship to get close enough to a black hole without crashing and then leave the system. So in part 1, the system was the star while the black hole in space were its surroundings, and in part 2, the spaceship is the system while the black hole, space, and star are its surroundings. For models and fundamental physics principles, we have Newton's second law, or the momentum principle, which is F net equal to dp over dt, or F net parallel plus F net perpendicular. And as you'll see here, this is the parallel component, then we have the perpendicular component and the gravitational force and how to achieve the mass of the black hole. And then in part 2, in my code, you'll see that I incorporate the velocity and position update formulas, which are written below. The methodology behind this lab was to edit the code based off the physics principles, run the code, and compare and contrast the model based off its data. The following here are a preview of my results from the lab. Now into the experiment itself. For the beginning of the code, I put the initial conditions, which you'll see in lines 122 and 125. Then for this part in line 163, the momentum formula is used, so P equals mv. Then in lines 167 and 168, change in velocity formula is used, so delta V equals V final minus V initial. And in line 174, Newton's second law is incorporated, so F net equals dp over dt. And the same follows for lines 182 and 188 for F net parallel and perpendicular. And lastly, in line 192, the formula was used to calculate the mass of the black hole. When I ran the code, these were my results, and here's what the computational model looked like. As you can see here, the pink is always moving towards the center of the orbit, and blue is always pointing in the direction of momentum. So the arrow grows larger because that's where the greatest amount of gravitational force is, and the arrow shrinks as they move farther away from the black hole. For part 2 of this lab, in line 31, I wrote the mass of the black hole, which was calculated from part 1, and in lines 61 and 62, the values written in the code were achieved through trial and error, or until the spaceship didn't crash. Continuing on to the rest of the code, the FNet for the planet was put in lines 78 to 85, and the FNet of the ship was shown in lines 94 to 104, and based on the position and velocity update formulas, we can go ahead and update the position and velocity of the spaceship and the planet. After running the code for part 2, you can see here that cyan represents the planet's orbit and the magenta represents the spaceship's trajectory. So here, nothing crashed, so the magenta represents the planet leaving the system, and the cyan is where the ship orbited, so that circle right there. Moving on to the discussion, some possible errors. So for part 1, it could have been inaccurate calculation of mass of the black hole or inaccuracy rounding for the gravitational constant. For part 2, if any calculation was done incorrectly for part 1, then there would have been a slight deviation for the spaceship's velocity. So for part 1, discuss how the net force and its parallel and perpendicular components are different from the rate of change of momentum and its respective components. So mathematically, F net, which is dp over dt, are the same value, but they represent different concepts. Net force and the parallel and perpendicular components are extrapolated from the rate of change from a momentum of the object, which will end up having the same value. For part 2, instead of wanting to take a quick look at the black hole and leave, you decide you want to enter an orbit around the black hole. So what initial velocity would your spaceship need to have in order to enter some orbit around the black hole? So for here, in order to determine the initial velocity of the spaceship, there are a few things we need to consider. You need to find the force that matches the force of gravity. Then there would be no net force and a constant velocity at the angle for this scenario to be achieved. So in conclusion, I was able to determine the initial velocity of an object to get close to its surroundings without crashing, and I was able to create a model to estimate the mass of the black hole while using the momentum principle for position, velocity, and gravitational force equations.